What do you think, Helen?
Maybe I can start. Yes.
Okay, cool. Yeah, hi everyone. Welcome back to another meetup with the Quantum Computing and Data Science in partnership with Warsaw and Washington, D.C. Quantum Computing Meetup Group. Today we have Dr. Pawel Gora. I'm sure many of you have seen him already. He's definitely around, community. But actually, he will be the speaker today, which is pretty cool. It's great to finally meet you, Dr. Powell. I know we always just do separate meetups, but it's the first time I think we've actually
Yeah.
uh, been
Yeah,
together at
nice.
one.
Yes.
Yeah, yeah.
Good.
So it's funny. Yeah, Sebastian too. Actually, Sebastian's never there, but he's here today as well. So it's good to see the Warsaw team. I guess I'm the Toronto team, so
Good.
good to see you. Yeah, so today the abstract, Dr. Pawel Gora will be presenting the results of his research on the optimization of complex processes. Some of them have been published in his doctoral thesis entitled Metaheuristics in Optimization of Complex Processes, which was defended on February 29, 2024 at the University of Warsaw. They're dealing mainly with optimization of road traffic in cities by controlling traffic lights and optimization of cancer treatment by radiotherapy. Um, Pretty interesting fact, those two complex processes have similar properties, allowing them to treat them with similar mathematical techniques. In the second part of his discussion, he will be presenting the results of his research on optimizing routing problems in logistics using reinforcement learning and quantum computing. Some of these results were achieved at the research group TensorCell, which he founded in 2017. Yeah, so quick bio. Pawel Gora, scientist and entrepreneur, founder and CEO of Quantum AI Foundation, researcher at the University of Warsaw, where he obtained a PhD in computer science in 2024. 2024, yeah? It said,
Yes. Yes.
okay,
Yes.
2024.
Just
Wow, yeah,
yeah.
congratulations, very recent this year.
Thank you. Yes, exactly.
Yeah,
Just 2 weeks
awesome.
ago.
Yeah, that's great. Yeah, and as mentioned before, he's the founder and leader of the research group TensorCell, dealing with the optimization of complex processes. He's the chairperson of the board of QWorld and the coordinators of one of his cousins, Q Poland. He's the advisor of several startups. Um, he's interested in new technologies such as artificial intelligence, quantum computing, and their applications in various fields, which include transport, medicine, and e-commerce. Um, he is the author of Traffic Simulation Framework Program for Traffic Simulation and Analysis, and the author of many scientific papers published at leading conferences and universities such as MIT, Stanford Research Institute, Cambridge University, ETH Zurich, and the University of Toronto. His work has been cited award many times. Was recognized among the top 10 Polish talents in the MIT Innovator Under 35 competition and was included in the New Europe 100 list among 100 outstanding innovators in Eastern Europe. In the past, he has worked as an engineering or research intern at Microsoft, Google, CERN, and IBM Research. He also, as part of Quantum AI Foundation, he co-organizes Warsaw AI and Warsaw Quantum Computing Group meetups, which we are partnered on, and organizes lectures, workshop, competitions, conferences, and hackathons on new technology. Yeah, that's basically the general gist of Dr. Pawel Gora, and I guess I'll just bring it back to him.
Okay, great. Thank you. Thanks. So indeed, it's good to be here again, but this time as a speaker. So actually, I was a speaker during this Washington Quantum Computing meetup already 3.5 years ago. So it's my second talk. So it's great. It's great to be here, and let's start. Let me just share my slides. So thanks once again for the introduction and for the invitation, Helen and Young. Thanks for that. Can you see my slides now?
Yeah.
Good, great. Yeah, so Jung has already introduced me and told about my affiliations. I just wanted to say that the research that I will present today was carried out at the Faculty of Mathematics, Informatics and Mechanics of the University of Warsaw, where I obtained a PhD degree earlier this year, just about half a year ago. And in the research group TensorCell, which is an independent research group that I founded several years ago. And the title is Optimizing Complex Processes Using AI and Quantum Computing. So I will be mostly talking about the AI approaches, but just at the end, I will tell how quantum computing can be applied in this domain as well. Because as you will see, I've prepared many slides, and some of this quantum computing part that I will be talking about at the end was also covered during my first talk during this Washington Quantum Computing meetup. Okay, so let's start. And maybe one more thing, if you have any questions, you can also raise your hand or write your question on the chat. So maybe the moderators can read the questions, and we can just try to make this lecture interactive. All right. So in the title of my talk, we have quantum, or we have complex processes or complex systems. So what are the complex systems and processes in general? So a complex system is a set of multiple components that can be some physical components or abstract components that interact to produce some emergent properties that are difficult to derive from the properties of these components. And a complex process is just the evolution of a complex system over time. And here we have some examples like road traffic. So these components are the vehicles or drivers, participants of the traffic, and they interact, they share the road infrastructure, and this interaction may lead to some emergent properties like traffic jams or car accidents. The society is a complex system as well. We have people who are in interaction, and this interaction may lead to discovering some new ideas or waging wars as well. Ant colony is a complex system. An organism is a complex system because in our organism we have many cells. They are also in interaction. They form some organs. These organs are also in the interaction, thanks to which we will live. So we have some living organisms. And these organisms may also form a complex system, which is a society. So in particular, the human brain is a complex system as well, because we have neurons that interact, and this interaction may lead to the consciousness or the process of solving problems, for example. And when we can also think about abstract complex systems or processes like cellular automata. The stock market is a complex system as well. So interaction between different participants of the stock market may lead to some financial bubbles or financial crisis. Okay, so these are just examples, and it's very interesting that even though these complex systems processes may appear and we may find them in totally different domains, they share some very interesting properties. So here we have the list of typical properties of complex systems or processes that are shared by most of the complex systems. Emergent properties, right? So this was already in the definition that I presented, right? So when we have many vehicles, there might be traffic jams. Conflicts between people may lead to wars. Interaction on the stock market may lead to financial bubble or financial crisis. Nonlinearity, which is a mathematical property, which basically says that the whole is greater or different than just the sum of parts, right? So when we just add the properties of the components, then it's not the same as the properties of the whole system consisting of these components. Sensitivity to initial conditions, so the so-called butterfly effect. When we observe the evolution in time, even when this evolution is deterministic, it might be impossible to accurately predict the future states of the system. Openness, so there might be influence from the environment. Adaptability, it's not in case of all the complex systems, but there is a family of complex systems that is called complex adaptive systems that are also able to adapt to the changes in the environment in which they operate. So, for example, in case of road traffic, when you have many vehicles, the drivers may adapt their route choices. They may decide to change their routes, and just in order to travel faster, right? So this is just an example of adaptability. Hierarchy. So I've present this hierarchy on the case of living organisms. So we have the living cells at the bottom, or maybe even the atoms or some chemical substances, which might be even lower. And the interaction between cells may lead to some physical operations of our organism, and cells just form organs and tissues. These organs are also in interaction, so that's why we can live. So we have living organisms, and these organisms may also interact, forming society. So this is an example of a hierarchy that frequently occurs in case of complex systems. Computational irreducibility. This is a very interesting property because it basically means that we cannot accurately predict the future state of the system in the other way than just by observing the evolution of the system, or maybe running a very accurate simulation. For example, if we have cellular automata, then we can run a simulation of the evolution, and then we can predict the state. But in case of some complex system, it's not possible. I see that Itamar has raised his hand, so I will let him ask a question.
Well, as usual, you mention evolution, and it's natural to ask a question that is very natural and simple. What's the role of time in the cooking of emergent properties?
Yeah, so this is very interesting. I'm not sure if we have a good answer for this. So because so what is the time in general? Because perhaps the time itself is an emergent property of some let's say physical properties at the low level of our real world. So it's really hard to say, but in general, when we ask about let's say classical complex systems, so not at the quantum level, but when we are talking about classical complex systems, then it doesn't make sense to think about emerging properties without the evolution, actually. So when we have just a given state, we cannot observe that the interaction has led to some emerging properties, let's say, right? So it's even difficult to say what is the interaction when we just observe the system and we observe only a single state at a certain time. But that we may have also some relativistic effects. So this is really difficult thing, and I can tell you that in my PhD thesis, I've even tried to formally define this, let's say, evolution of the complex systems in time that may lead to emerging properties, and I've only managed to do it for classical systems. So just I had to neglect relativistic effects and so on. So, but in general, in my opinion, it's a very difficult question.
Okay,
but this is a very good question.
And beautiful response, but I want to expand now. If I'm looking at the world as, and all your examples, as a manifestation of networks, what about networks that are not uniform in their properties? Namely, part of the network is strongly nonlinear, some of it is simple and linear, and all kinds of varieties or variations along and across the network. So there are some treatments of networks, call it synonymous to graph. And what's the power, what's the magic of graph theory to simplify these things? So Maybe it's not a question, maybe just playing with words here. I'm not expecting
yes,
an overall answer to this.
Yeah. So regarding graphs, later in my talk, I will tell how I managed to take advantage of some, let's say, properties or the fact that we have a complex system operating on a graph. So then I will tell you, and I will present how I took advantage of this to optimize a complex system. So namely the road traffic in cities. Taking into account the fact that we have the underlying graph structure. Because in general, almost everything can be modeled as a graph. I agree. So this is also one of the reasons why potentially the approach that I will present later during my talk could be has a good generalization properties, right? So it could be potentially applied to some other domains. So let me come back to this question later when I will be talking about graph neural networks that were applied to model. So in some sense to model complex processes. Okay.
Okay.
I'll come
Thank
back
you.
to that. Yes. Good. So the last property that I listed here is the order in chaos, because in general the complex systems are usually described as something between the systems that are totally predictable and easily predictable, for which we have some relatively simple equations, and we have some analytical formulas to calculate the future states, and a random behavior for which we can just carry out some analysis on a statistical level, right? So in case of complex systems, sometimes the systems might be deterministic, but due to this sensitivity to initial conditions, we might not be able to accurately predict the future states. So as you can see, so these are very interesting properties, and I've already told you that some examples of complex systems and processes exist in different domains. So for me, it was a fascinating universality and omnipresence. And that was one of the reasons why I decided to investigate this domain and started thinking how to optimize complex processes. So at the beginning, I focused on road traffic in cities because I've been already working on modeling road traffic in urban areas, and I knew that it's a very serious commercial and social civilizational problem. So, for example, the annual cost of traffic jams in Poland is estimated to be about 4 billion Polish zloty, which is around $1 billion per year. And this is just a estimated cost of wasted time and fuel in 7 largest Polish cities. So I know that in the US, it's estimated to be about 230 billions per year. So that's really a lot. And this cost doesn't take into account some other factors like air pollution, for example, right? And it's also estimated that air pollution shortens global life expectancy by 2 years. Moreover, we have car accidents, and every year more than 1 million people die in car accidents, and more than 20 million are injured. And there's also a huge cost of car accidents. So in the US, it's more than $230 billion. So that's really a lot. So I already observed that this is a serious commercial and civilizational issue. So this was a good let's say research problem to tackle, right? So how to improve road traffic in cities. So let's first focus on traffic jams, right? And let's assume that we have this question: what is the reason for traffic jams? If you have some ideas, I believe that you might have some ideas. What's the reason? You may just write some answers on the chat or raise your hand if you want.
Because of narrow road, like that path is narrow, and that's also overcrowded.
Overcrowded, yeah, too many cars. Okay. Yes. Any other ideas?
I'll just comment a bit.
Yes.
The route is narrow.
Accidents. Yeah. Wrong calculation of flow traffic. Okay. So in general, alcohol. that's a good answer as well.
But I'll just comment that, Pavel, I think some questions I was about to ask earlier is to do with the variables. So in the trying to predict the complex system, isn't it a question of understanding the variables? So like the question that you're asking now, the reason for traffic jams, is like asking what are the variables which cause the traffic jams? So it could be associated with the working hours, peak times or not peak times, working hours could be associated with events, particular event, and so on. There are variables. So it may be that is associated, it's a problem of events, isn't it?
Can be as well. So there are, so in general, there might be many different problems and many different reasons. And each reason might be different. So there might be car accidents, there might be some road works, there might be just too many cars. But we can, all these issues or reasons can be formulated using this inequality, that the demand for using the road infrastructure is greater than the supply, so the quality, the capacity of our road infrastructure in this case. So when we have car accidents, then the supply is worse than the normally. When we have too many cars, it means that the demand is too high. And usually, so you know from the economy that when the demand is higher than the supply, then usually the cost of using something increases, right? So in this case, the cost of using the road infrastructure increases. So in order, when we look at this this way, so what we should do to deal with it, right? So we can try to decrease the demand or improve the supply, and all the approaches to deal with traffic jams rely on one of these two actions, let's say. So when we are talking about reducing demand for road space, we can just introduce some entry bans, or there might be some charges or fees for entering some areas. There might be, let's say, intelligent GPS navigation to tell the drivers that they should just choose another route, or that they should start driving a bit earlier or a bit later. We may introduce public transport. So there's then when the public transport is good, then there's lower demand for using private cars. We may have shared rides, shared vehicles, shared bikes. But we may also think about improving supply, like building more roads or improving traffic light control. And I think that many of these ideas have already appeared on our chat, or the problems related to this these ways of improvement have already appeared on our chat. So in my research, I focus on traffic light control, but I've also carried out some research with several other options. So, for example, when we think about building new roads, of course, we can try to do it, but maybe you have heard about it, and I will also come back to it later, because when we start talking about quantum computing algorithms, that there is a famous Brace paradox. I believe that some of you have heard about it, and it basically says that building more roads is just not enough. So when we build a new road, it doesn't mean that the traffic will be better. So here is just an example, right? So let's assume that we have some numbers, let's say 4,000 drivers driving from start to the end, right? And on some links, the travel time is proportional to the number of cars passing through this link, which is reasonable. So this is just an approximation, but in some ranges of the traffic density, it's quite accurate. And some roads are quite wide, so that there might be many lanes, and we can assume that the travel time is just constant. So initially, when there is no link between points A and B, then about 2,000 drivers will select the road going via point A, and 2,000 drivers will select the second route going through point B. So the total travel time will be 45 plus 2,000 divided by 100, so it's 65 in both cases. And this is the so-called Nash equilibrium from game theory. So in case of transportation, it is called the wardrobe equilibrium, which basically says that this is just a state in which it doesn't make sense for any driver to change its route, right? Because when you have 2,000 cars going through A and 2,000 cars going through B, then any change, so if one of the cars, one of the drivers decides to change a route, then their travel time would increase. But what will happen if we just build a connection between points A and B, and we can even assume that the travel time is 0. So we just built a new road, and it's a very fast connection. So then drivers who initially traveled through point B will figure out that it may take more sense for them to travel through point A. But if all the drivers made the same decision, then 4,000 drivers will go through A and then to B and here to the end. And the total travel time will be 80. But again, this is a Nash equilibrium. So as you can easily check, if we have 4,000 drivers going first to point A, then to B and to the end, it doesn't make sense for any of them to change their strategy because their travel time would increase. So that's why this is a paradox, and it's not only a theoretical case, because such issues have already appeared in some real road networks when some new roads were built, and it turned out that all drivers wanted to use a new road, and it led to just blocking some other roads in the road network. But there were also the opposite cases. So there was a highway in Seoul in South Korea, and the traffic engineers made some analysis, and they come up with an idea to just destroy this highway or close it. I'm not sure how exactly it was implemented, but they just calculated that if there were no highway there, then the traffic would be better. And indeed, when they did it, the traffic improved. Okay, so we know that, but of course, it doesn't mean that we shouldn't build new roads. We should build new roads, but we have to do it in a smart way, and we have to do traffic analysis, right? So we need to have some mathematical models of traffic, run simulations, and each time we just have to check what would be the state of the traffic. So it's also good to mention that there are different approaches for traffic modeling. So there are macroscopic models, which usually describe the relationship between some aggregated characteristics of traffic, like speed, density, intensity, so congestion, traffic flow. And usually they are based on analogy to other physical phenomena, like fluid dynamics or kinetic theory of gases. There might be mesoscopic models in which, or maybe I will first tell about microscopic models. So in microscopic models, each vehicle is represented as a separate object, and at each step of the simulation, the speed, position, and maybe also some other variables like acceleration of a car are just recalculated based on the previous speed, previous position, and maybe also some attributes of other vehicles or attributes of traffic signals. And finally, there are intermediate models, the so-called mesoscopic models, in which vehicles travel in some homogeneous packages. So it's similar to the internet traffic, I would say. And the speed is constant between, when these packages of cars just move from one intersection to another, and the speed just changes during events like turning at an intersection. Okay, so in my research, I focused on microscopic models that were based on cellular automata. I see that there is a question from Sunil, and there were also some questions on the chat, so let's maybe take some time to answer.
Yeah,
Sunil.
this traffic model you created by yourself, or is inbuilt model that
I will tell you. I will tell soon about the traffic model that I used and I extended. Okay, so I will tell it on the next slides.
Okay, thank you.
Okay, all right. So the model I used was based on cellular automata. I believe that some of you have heard about cellular automata, and in particular the Game of Life of John Conway. So in general, cellular automata, and actually I've already told you that cellular automata are just also examples of complex systems or complex processes. So cellular automata are, let's say, systems or sets of cells. Usually, these cells are just located in one-dimensional, two-dimensional, or three-dimensional space that is just divided into cells using a grid. So let's assume we have a grid here, and each cell, at each time, each cell has a state. And there are some rules specifying the evolution of cells. So how the state of a given cell should change, or what would be the state of a given cell after applying specific rules. And these rules usually take into account the state of that cell at the previous step and the states of the neighboring cells. So this is a typical setup of cellular automata, but there are also there might be also some exceptions. So the cellular automata do not have to be defined only on a grid and only on 1 or 2 or 3-dimensional spaces. So they are more general concepts. It's also maybe good to mention that the cellular automata were discovered by Stanisław Ulam and John von Neumann when they were working together in Los Alamos in 1940s. There have already been published some research articles presenting traffic models based on cellular automata. One of the simplest but very interesting traffic models is the so-called Nagel-Schreckenberg model. So it was proposed more than 30 years ago, and it is a one-dimensional microscopic model. So there the idea was just to model traffic and simulate traffic on highways. So, and without, with just a single lane on a highway, right? And it was a probabilistic cellular automaton. So this one-dimensional tape was divided into cells. So it was assumed that the length of a single cell corresponded to about 7.5 meters in case of real world, in case of real roads. Time and speed are discrete, and each cell can be empty or can be occupied by at most one car. So as you can see here, right? And cars are indistinguishable, so they have exactly the same rules and rules of updating the position and speed. They have the same maximum speeds and so on. And the state of a cell can be null if there's just no car, or it can be the number of cells the vehicle passed through in the previous step. So like 0, 2, 1, and so on. All right, and these are the rules. So these rules are relatively simple and intuitive. So first, every car, every driver tends to accelerate, right? To just drive as fast as we can, but not to exceed the maximum speed, right? And of course, there is a safety condition, because when there is a car in front of us, so you can see that there's only one lane, right? So it was not possible to just overtake another car. So we have to reduce the speed, and we need to take into account the distance to the nearest car in front of us. Then with a certain probability, that was usually quite small, the speed can be reduced further by 1 unit, but again, not to be below 0, of course. And it has been proven that this is the step is necessary for to model the spontaneous formation of traffic jams, which really occur on highways. And finally, the car moves forward the VI number of cells that was calculated after these 3 steps. And these rules are applied synchronously to all the cars that are already on our road, our one-dimensional tape, one-dimensional cellular automaton. And what is very interesting, so one of the interesting properties of this model was that it was able to quite accurately reproduce something that is called fundamental diagram of traffic flow. So this fundamental diagram is a diagram presenting the relation between traffic flow, so number of cars passing a given point in a given time unit, like hour. So relation between flow and the traffic density or occupancy of roads, right? So the number of cars per site. So this is here we have data from real traffic. I think it was a measurement in Germany. And here we have the results of simulation. So you can see that there is a peak around, so a bit lower than 20% of the occupancy, which means that when we have about 1 car per 20 meters, then the traffic is still quite smooth. But when we increase the density, then the flow is no longer linear, unfortunately. But as you can see, for the same values of the density, there might be also different levels of traffic flow because of this non-determinism that we have in the model and in the real traffic, of course. Okay, so I used this model, but I extended it. I extended it to model to simulate traffic on arbitrary road networks, so arbitrary graphs, directed graphs representing road networks. So yeah, I used directed graphs. At some intersections, at some nodes of the graph, there were traffic lights located. The edges of this graph were divided into lanes that were later divided into cells, as in the original model. And the movement on edges was according to the rules of this Nagel-Schreckenberg model that I described, but with some modifications. And there was also, for example, the speed reduction before the intersection or before turning, or of course before red light at the intersection. There were different profiles of vehicles. There were different types of roads with multiple lanes, different speed profiles. There were different profiles of distribution of the origin and destination points. So there were many extensions that I've introduced to this model. And finally, I've implemented this model in a software that I've called Traffic Simulation Framework. And here you can see just a graphical user interface of this tool with a map of Warsaw, and these red dots are just locations of cars just before starting the simulation, right? So we can set some values of the parameters like the number of cars, number of steps, and acceleration, some turning penalties, so how the speed should be reduced, and so on. So I've implemented many features, and it's not that important what were the exact features implemented there. I would just wanted rather to tell you about some interesting research that was done using this tool. One of the first interesting researches was on just predicting road traffic. So predicting some traffic characteristics like traffic congestion, number of cars, or travel times at different road segments. So for example, in one of the papers already many years ago, we used Bayesian networks. So to just that took as an input some traffic characteristics from some road segments and aimed to predict some traffic characteristics at some another road segments, right? And there were quite good results with this Bayesian networks approach. So later I co-organized an interesting contest. So it was a competition organized with the IEEE ICDM conference already in 2010, and TomTom, one of these GPS navigation companies, was one of the sponsors. And then there were three tasks. So first, I just generated very large data sets. So there were really tens of thousands of hours of simulations using the tool that I've developed. So there were large data sets, and these data sets were made available to the data scientists. And the goal was to predict traffic congestion, travel times, and the order of occurrence of traffic jams. And there were more than 600 participants. What is quite interesting was that here you can see a nice photo of the organizers, of winners of this competition. And here the guy who is the third from the right is Benjamin Hamder. So it's a person who founded the Kaggle, which is a platform for running similar data science competitions. So together with my colleague, we were later joking that maybe he was inspired by our contest. It was already 2010. But there were also participants from IBM, from some other good research laboratories, AT&T Labs, and some good universities. But later I started working on something that I called what-if prediction, right? Because I observed that, okay, there are already so many research works on predicting travel times or predicting traffic congestion that there are really many research laboratories working on it. But what seemed to be more interesting were the questions like, what may happen if we change something in the road network? So for example, what happens if we change the traffic light settings? So as you can see, it's a step towards traffic optimization, right? So it's not only traffic prediction, but now we can start talking about traffic optimization, because if we can accurately give precise answers to these questions, then we can potentially just explore a very large space of possible, let's say, traffic light settings or some other changes that we can introduce, and find the settings that would be best for our road network, right? So that was the idea, and that's why I observed that this is already a step toward traffic optimization. Okay, so what are the good tools for this traffic prediction? So of course the most popular tools are just traffic simulators, like the one that I've developed, because we can just introduce the changes in this digital twin of the road network of the real traffic. We can introduce some changes, we can run the simulations, we can collect the output, and then we can say that we evaluated and we evaluated the change, right? And you can say whether the traffic is better or not. But the problem is that the accurate traffic simulations are time consuming. So especially on a large scale, like the whole city, like Warsaw or Washington or New York, when we have tens of thousands of cars and thousands of intersections, thousands of connections between intersections. So it's really time consuming. And in some cases, like for the optimization procedure that I've described, we would need to run a large number of simulations with different settings, right? If you want to find the best setting, then we would need to run a very, very large number of simulations. And for some models, these simulations can be stochastic. So even for a single setting, we may need to run or repeat our simulations many times. And just to give you an idea how difficult and how complex this problem is, so the total number of possible signal settings in Warsaw, where we have about 800 intersections with traffic signals. So even let's assume that the durations of red lights and green lights are constant, but we only change the offsets, right? So the differences of the first time when we just do the switch from the red signal state to the green signal state between each of these, let's say, 800 intersections. And let's assume that for each intersection, we have 120 options to set this offset because the whole cycle is 120 seconds. So then the number, the size of the space of possible settings is more than 120 to the power of 800. So it's much more than the number of possible games in the game of Go, and much more than the number of atoms in the visible universe, right? So in such a large space, we would like to find the optimal setting. So we can see that it's quite a difficult problem, but okay, so very often we have some optimization problems, which when the sizes of the spaces are very large, but we do not have to explore all possible settings, because we may have some, let's say, analytical formulas that can just give us the optimal points. Like let's assume that we have the x square function, so we can easily, so the domain of this function is infinite, but we can easily find the minimum of this function. But unfortunately, it has been proven for very simple mathematical models of traffic that this problem is anti-hard. So most likely would not be able to really find the optimal, the best possible settings for given traffic conditions, even in very simple mathematical models of traffic. But now the two interesting observations. So first observation is that we can only do such optimization in some virtual mathematical models. So the settings, even if we find the best settings in the mathematical models, then it doesn't mean that these settings, the same settings, will be best for the real traffic, because the mathematical models are only approximations of the real traffic, right? So maybe instead of just looking for the optimal solutions, maybe we can try to look for some, let's say, suboptimal or heuristically optimal solutions that can be worse by maybe 1, 2, maybe 3% than the optimal solutions. But in such a large, very large space, perhaps there might be much more settings that are someone needs to mute, I believe. Okay, so in such a large space, we should probably have much more settings that can be slightly worse than the optimal solutions, but maybe still acceptable for us. And if they're acceptable in the mathematical model, it's hard to say if there will be better or not in the real world, but there's, let's say, quite good chances that they will be good enough. So this is one thing. Another thing is that even if we find good settings for a given traffic state, the state of traffic in 1 or 2 minutes from now might be totally different because of this, let's say, non-determinism and some car accidents and so on. I see that Itamar has raised his hand, so Itamar, please. I think you are muted now. I'm not sure. Yeah, Itamar is muted. And Mark also wanted to ask, so maybe Mark, you can go first.
Yeah, do you hear me now?
Yes, Itamar, I can hear you. Mm-hmm.
Yeah, I have a question. You spoke about so many equations and so on, and new way to deal with it, but how about dimension reduction?
Mm-hmm. Yeah,
Is that valid here to try?
can be valid. So potentially, maybe perhaps instead of considering every possible setting of traffic signals at a given intersection, we can think about different settings, but assuming that the differences between them are at least 5 seconds, right? Because maybe 1 or 2 seconds doesn't make a huge difference. So we can already reduce it, and we can also try to, let's say, cluster our road network into into some subnetworks and try to solve this problem in smaller areas.
Yeah, subregions. Yeah.
Yes, subregions, and then so apply something like divide and conquer technique, right? And then build a solution for the whole city. So I've go toward this direction, right? So I will tell you later, because I will tell you that I run experiments on a much smaller area with only 21 or up to 42 intersections, right? So I will indeed, this is one of the things that I did. But again, then the question is that the question is how to merge this solution for subregions. So first of all, how to divide the road network into subregions, into clusters, and
The solution will depend on this kind of division rules.
Yes, exactly, because intuitively, a good clustering would be to just divide into this road network into clusters that are highly connected inside, so they're highly interconnected, but there shouldn't be too many connections with some other clusters. So that's the intuition, and there are some metrics in graph theory, and actually there's something that is called the Chigar ratio. I heard that was also used by Google to cluster the internet. So there are such approaches, and indeed this is you have a very good intuition that this is something that we should do. But anyway, even if we reduce it, then the space is still very, very large, and we have to deal with it. So the problem still exists. Yes, Mark, or maybe Itama wanted to say follow up.
Yeah, I wanted to make 2 comments. One, this is a reference to another problem that is known in the US election system, that the districts are divisions can affect the results of the whole elections, and it's a very complicated system there. That's reference 1. And the question comment that comes here when I hear about this model approach is, how about macroscopic, microscopic fluid dynamics? And agent-based modeling as two alternatives that are probably considered by other people.
Yes. So I can give the answer to the second question, because actually I've also tried mesoscopic and macroscopic models for this, but there was so I will tell about it later. But in case of mesoscopic models, they were much faster, but the quality of the output that they produced was not sufficient for me. But I only tried one mesoscopic model. But I know that there are many other mesoscopic models, so probably we can still look for some other models. In case of macroscopic model based on differential equations and analogy to fluid dynamics, we've also implemented it, but so the problem is that these differential equations do not have simple analytical solutions. So in order to find good solutions, again, we have to rather try some approximate approaches, and finding good solutions for this is also time consuming. So we've observed that, let's say, the required time is more or less the same. So we haven't observed that there is an advantage.
Thanks.
Yeah, thanks. I think that Mark wanted to ask something. Yes, Mark?
Yes, Dr. Gora. Do you think if we were able to reduce the variability of the nature of driving in itself, like let's assume that we didn't have any steering wheels or we didn't have speed control, would it bring down the complexity of this system?
Perhaps. So I believe that the speed control might slightly reduce the complexity, but anyway, so there might be I think that this could reduce, because maybe we could assume that all the cars just travel with more or less the same speed, which is close to the maximum speed, right? But anyway, if there is large congestion, then the speed can be much lower than the maximum allowed speed. So that's still something that we should model here. So there's always a question about the accuracy of the model and conformity of the model with real world traffic. So this is the problem, because when we reduce the complexity of the mathematical model, then it turns out that its conformity with real world is not as good, because so the problem is that the real traffic is quite complex. If we want mathematical models to be accurate enough, then they cannot be too simple, let's say. So I believe that there is a certain level of complexity that is necessary to accurately model traffic.
I just have another quick question. So what are the ways in which you think might bring down the complexity of this problem? And let's say, for example, we have speed limits, right? That would control this. But what are the other ways you think?
Yeah. So I believe that what Itamar mentioned. So let's say we can. So instead of considering all possible settings of traffic signals, we can maybe consider only settings that are different at least by 5 or 10 seconds, for example, right? And assume that maybe 5-second difference or 2-3-second difference is not that much. So as you can see, it will reduce this value. So instead of 120 seconds, we may have something like 10 or 12 here. And again, instead of looking for the whole area at the same time, like the very large city, we can think about some subregions, right? And then try to solve the problem in some subregions for the intersections that are close and they are really connected. So there are interactions between traffic at this neighboring intersections, let's say, right? But when some intersections are very distant, they are in totally different regions of the city, then they are not so they do not infer each other, right? So they do not the impact on each other is not that high. So it makes sense to just think about smaller areas, and this is exactly what I also did in my research. But again, the problem is that that even for such after such reductions, the problem is still NP hard, and if we want to find good solutions, then even to evaluate the quality of different settings, we have to run some simulations, right? And as I told you, the model that I used, so that was this Nagel-Schreckenberg model and its extension. As you can see, these rules are very simple. Sorry, these rules are very simple, and they were able to reproduce some real traffic phenomena. And when you think about some even simpler model, it may turn out that this accuracy of the model is not good enough. The conformity with the real traffic is not enough. I think that in case of this Nagel-Schreckenberg model, I'm pretty sure that it has been already proven that if we remove just a single rule from this set of simple rules, then this model will not be able to reproduce real traffic accurately, right? So, but anyway, this is a very good question, and in the next on the next slides, I would like to tell you how I approach this problem. Okay, and because I had to solve it, and I would like to tell you how I did it. Okay, in my research. Good. Okay, so let's move forward. So, in such cases, when we have when we do not have to look for the optimal solution, but let's say suboptimal or heuristic solutions are sufficient for us, then we can use something that is called metaheuristics. So these are just some optimization algorithms which are used to find near optimal solutions. And unlike some traditional optimization algorithms which rely on mathematical formulas, metaheuristics use some heuristics to guide their search for solutions. So this is just an example. So first I give you an example, and later I will just show you a pseudocode of a general metaheuristic algorithm. So an example is a genetic algorithm, right? So first we encode our space of solutions into genotypes. So in this case, we encode configurations of traffic signals into genotypes. So we have a set of some genotypes, and then we evaluate their quality, we select the best, then these best genotypes are crossed with each other, so we exchange the genetic material. For example, we take some parts from the one solution, another part from another solution, like some settings from one area in the city and some settings from another area in the city, for example. Then there can be mutation, right? So with some probability, we introduce some random changes to our genotypes. And then we just produce a new set of genotypes, which in theory should be somehow better, more fit, right? So because the whole idea is just a implementation of or inspired by the process of natural selection, where these different organisms, so in this case, different solutions, are evaluated. So their quality is evaluated, and just the fittest survive, basically, right? So the best of them are selected, and they produce the next generation of solutions in this case. And when we repeat this procedure in many iterations, then indeed, after many iterations, we can observe that there are some we are able to produce significantly better solutions. But anyway, even for such algorithms, we have to evaluate their quality using computer simulations. But it solves our problem of let's say finding heuristically optimal instead of optimal solutions. So if you are interested, this is a pseudocode of a general metaheuristic algorithm. So we need some kind of a fitness function. So in this case, the values of the fitness function are calculated using computer simulation, using traffic simulation. We need to have a stopping criterion. We need to have this transition rule. So these transition rules in our case are this selection, crossover, and mutation operators in case of genetic algorithms, of course. We first generate a set of initial solutions. They are evaluated using our fitness function. We have the best solution, and we generate a set of new candidate solutions using this transition rule and evaluate the objective function on elements from this new set, replace the current set of solutions with the new set with our next candidates, and so on. So we repeat it until some stopping criterion is met. So this is just a general pseudocode for metaheuristic algorithms. Okay, and I performed some first experiments with genetic algorithms already several years ago, and it already produced a reduction of waiting times at red lights by more than 3% compared to the best solution in a very large, but randomly generated initial population. Okay, so I already showed that it works, right? So thanks to this genetic algorithm, I was able to find slightly better setting than the best setting in a large randomly selected set. But the problem was that the time of running a single simulation of 10 minutes of real traffic in Warsaw was about 2 minutes on a standard machine. So that was too long. So then I started thinking about accelerating the computations, right? So of course, I optimized the code. I even tried to parallelize simulations on GPUs because cellular automata, as you can imagine, couldn't be potentially parallelized on graphical processing units, right? Or we can run computations on a cluster. Some parts of the genetic algorithm can be parallelized as well because we can evaluate the qualities of different signal settings in our single population for a genetic algorithm independently, right? So that's why we can use clusters with many CPUs. I was also working on mesoscopic models, so not agent-based, not microscopic, but at a bit, let's say, higher level. And I also started running experiments on smaller areas. But what were the effects? Of course, I ran thousands of hours of calculations, so a lot of knowledge was gained. And the software was already quite optimized, so the reduction of calculation time was from 2 minutes to about 20 seconds. That was already quite good, but still too low for real-time optimization. but it was already quite good for some offline calculations, right? So I believe that this microscopic traffic simulator that I've developed is probably still one of the fastest microscopic simulators. And the mesoscopic model, which was, let's say, more general, so based on this packages traveling with a uniform speed, it turned out to be much faster. So the evaluation took about just a few seconds, less than 10 seconds, but it was not very accurate. So when I compared the outcomes of the simulation using microscopic model and this mesoscopic model, there was a difference of at the level of 20%. So I thought that, okay, it's not enough, right? Because this model will not be able to tell me which signal settings are really good. So 20% is just too large error. And unfortunately, when I tried to optimize settings on just a smaller area, it turned out that due to such an optimization, the traffic on some neighboring other areas may become worse, which is quite intuitive, right? So when we just focus on optimizing signal settings on one area, then it's natural that the traffic on that it is at the cost of worsening the traffic on some neighboring areas, for example, or it may happen. So that was a typical, let's say, default outcome that I observed after running experiments. I was also working on improving the model accuracy, right? So I collected some traffic data from urban road authorities in Warsaw. I tried to contact some other traffic data providers like Google, TomTom, but at that time they were not interested in sharing the data that I needed. So I started working on estimating the origin matrix, destination matrix, which basically contains information about from where to where people travel in the cities. So of course I gained a lot of knowledge. I built, so the microscopic model was more accurate, and the compliance of traffic volumes with reality, with real traffic, was satisfactory. So in traffic engineering, there is a metric that is called GEH. So it's basically a metric comparing different traffic congestion. So number of cars traveling through some road networks. It turned out that, and there is a threshold for this GEH metric, below which we consider that the model is already accurate enough. And I was able to achieve this level with this traffic simulation framework software. I also implemented some new functionalities. There were some new applications. So this was one of interesting applications. So I was contacted by some researchers from Technical University of Madrid who are working on finding the optimal location for a bridge in the border area between the Senegal and Guinea in Africa. So, and the problem was that there was almost no information about road networks. At that time, that was about 2015, 16, no, maybe later, about 2017, 18, and the publication was in 2021. There was no information on OpenStreetMap or Google Maps about road networks at that area. So that was quite tricky how to model traffic there. We're also working on recognizing the traffic states using machine learning models, just to predict whether we have a traffic jam or whether there's a free flow or not, based on some data from traffic measurements. But finally, coming back to this traffic signal optimization, I come up with an interesting idea. So the idea was that I can start approximating these time-consuming traffic simulations with machine learning models. So first, I use this traffic simulation framework tool to generate a large set of elements. So each element corresponded to just a single setting of traffic signals at 15 intersections. So it was already relatively small area. Of course, the size of a space of possible settings was also much smaller than for the whole city. And that was the input. So this setting of a traffic signal was an input to the simulator, and the simulator computed the time of waiting on red signals in this area with 15 intersections, right? So this was run for more than 100,000 different settings of traffic signals. Of course, the set was divided later into a training set and a test set. Each simulation lasted, or each run simulated about 10 minutes of realistic traffic with 42,000 cars. Okay, and then I started training neural networks on this generated data set, right? So in order to just replace the time-consuming simulator with a neural network that could be inferred much faster. And the results were very good. So we called this tool for approximating simulations tensor traffic. So the first version was implemented in Torch, not in PyTorch, but in Torch, because it was 2016, even before the first version of TensorFlow was released. So I had a colleague working at Google Research, Karol Kurak, and he was already quite experienced with Torch programming language, and he helped me implement these first neural networks. And already the first experiments were very good. So the mean absolute percentage error on the test set, so that was the error of approximating these time-consuming simulations with neural networks, was below 2%, while the maximum error on a test set was below 11%. So as you may remember, I told you that in case of this mesoscopic model, so the simpler model of traffic, the error of approximation was more than 20%. So these neural networks tend to be much better approximators of this quite complex microscopic simulator. And after training, the inference time was below 1 millisecond. So that was already very, very fast, a few orders of magnitude faster than just by running simulation. But of course, there was a quite huge time required to first generate the training set and then to train the neural networks on that data set. I see there's a question from Anne. So please go ahead.
Yes, thank you. I'm sorry to interrupt you. I wanted to ask, on the Warsaw simulation, how many traffic lights were you calculating for?
Yeah, so in these experiments that I'm now explaining, there were 15 intersections. So I focused, I used this idea from Itamar as well. And in order to reduce the complexity, in the first experiments, I just focused on much smaller area with only 15 intersections. Mm-hmm.
Thank you. Thank you.
Okay, yeah. And it turned out that even some small neural networks with fully connected, so not very fancy architectures, with several hidden layers with several hundreds of neurons in each layer are enough for this. And also live GBM models gave quite good results. We also tested many other machine learning models, but they were not as good as live GBM and neural networks. And the paper about this was published at the workshop of the NIPS conference. So now this conference is called NeurIPS, of course. And we also analyzed the distribution of this error on the test set, right? So we observed that, okay, this distribution is close to the normal distribution. So for most of the points on the test set, these errors are close to 0, so below 5%, right? So that's quite good. This is quite good. So then we just integrated this trained neural networks with the optimization algorithms. So not only metaheuristics, like genetic algorithms, simulated annealing, memetic algorithms, CMA, ES, and so on. We even use gradient descent. So that was a very good idea. And it also gave us very good results because, so the gradient descent is an approach that we use to train the neural networks. But when we have the neural network that is already trained, and we want to, because actually in this problem, we wanted to find the inputs to the neural network that would minimize the outputs. So we came up with an idea that, okay, so we have a function that takes these inputs and calculates the outputs. But this function is differentiable. So now we can calculate the gradients, but not in the space of weights of connections between neurons, like we usually do in case of training neural networks. But instead, we can calculate the gradients for the inputs of the neural network in order to find the inputs that would minimize the outputs from the neural network, right? So that was the idea, and it also gave very good results. And it was not possible to do in case of light GBM or other machine learning models, but for neural networks, it gave very good results. So for this, because I already had a publication at the NIPS conference, so I was able to build my research group that I called TensorCell, and together with these new researchers, we've really conducted thousands of experiments for different areas in Warsaw, for different values of hyperparameters, of the surrogate models like neural networks and optimization algorithms, and with some additional input data. So not only offsets, but also durations of signal phases. I see that Ram has raised his hand, so Ram, please.
Yes, hi. This is a great talk. Thank you very much. You said you were wondering and investigated what inputs would minimize the outputs. What do you mean by minimizing the outputs?
Yeah, so because what was the neural network here? So the input to the neural network were the settings of traffic signals, and the outputs were predicted times of waiting and red signals. So these were just some numbers in seconds, right? Like 30,000 seconds, time of waiting at red signals. So we wanted to find the inputs to the neural networks for which the neural network would return the minimum output.
Oh,
right?
okay,
So,
sorry. So you're
yeah.
not the... Okay, I understand.
Good. Okay. Yeah. So that's why we calculated the gradients in the input space instead of calculating gradients on the space of weights, as we usually do with the backpropagation algorithm when we train the neural networks. But of course, first we had to train the neural networks using backpropagation. But once the neural network was trained, we were able to calculate the gradients on the space of inputs. So that was the idea. Even though here is a star, because as you can see, the space is discrete. But of course, we assume that, but the neural networks, so contrary to the simulator, the neural network can take arbitrary inputs and it can still produce some reasonable outputs, right? So we just assume that this space is continuous here. And of course, the function was differentiable because that was just a neural network that is differentiable by definition. So we are able to calculate these gradients. All right, so I've told you about these optimization algorithms, and we've really run thousands of experiments. And here are some conclusions from these experiments. So it turned out that among all these optimization algorithms, the population-based algorithms in which we, let's say, evaluate large numbers of different settings at the same time and then try to generate new candidate solutions based on the results of evaluating quite a large set, usually give the best results. So I think that this gradient descent algorithm was the only exception. But simulated annealing gave relatively poor results in this case. And it's possible to find much better signal settings than the best settings in a large randomly generated set. So this approach is much better than just randomly sampling very, very large of settings from this very large space and hoping that we'll have a very good setting in this space, because the local optima or the settings that are really good are still relatively rare in such a large space. So in the case of neural networks, for some reason, the hyperbolic tangent activation function gave us the best results. So we just had some hypothesis why it's the case, but we still cannot be sure why we achieved such results. But what is also very interesting, that we also applied something that we called a trigonometric transformation of the input data, because the input data, again, were the offsets, right? So these times from the beginning of the simulation to the first switch from the red signal state to the green signal state. So that was a time in seconds. And that was so for each intersection, we had just a single value from this set, right? And even after normalization, when we normalize it to the range 0, 1, for the neural networks, so when we trained the neural networks, they learned that they thought that the values 0 and 119 are the opposite values, right? So they are totally different because they are two extremes. And one of the consequences was that our optimization algorithms tend to find local or the optima, to candidate solutions close to the border, so close to these extremes. But later, after analysis, it turned out that these are just the areas in which our neural networks do not give good approximations, right? So the errors of approximation are much larger there. So we come up with an idea to just learn or to just teach our neural networks that these settings of traffic signals form a cycle. That in fact the offset 119 is just a neighbor of 0, right? Because we have a cycle. So in order to do it, we applied something that we call the trigonometric transformation. So basically, we just put these points from the input space on a cycle, or actually on many cycles, right? So for a single intersection, these were just the points on a cycle. So we have sinus and cosinus trigonometric functions, of course, and it improved the results. So that was a very good idea. Of course, there were many other ideas that we've tested and they didn't work, but this idea worked very well in this case. And we also extended the input. So instead of just having only the offsets, we also assume that we may have different durations, different lengths of the phases, different durations of red and signal phases. So then, of course, we needed much larger training set with more than 1 million elements. And what was very interesting is that some much larger models like BERT, based on transformers, were necessary to still achieve very good results, because the space of possible solutions was much larger. So even for the problem that we're solving at the beginning, that was still a simplification of the actual problem. And what is also very interesting, and we still do not know why, we still cannot fully explain it, is that when this BERT model was pre-trained on the natural language, and then it was trained again on our data set, it gave us very good results. But when it was not pre-trained on the natural language, but there was just a random initialization of the weights of connections, then we were not able to achieve good results of training. So it turns out that even though the problem of this approximating the outcomes of traffic simulations is totally different than the problem of analyzing the natural language, pre-training such language models on a natural language data set can help us solve some other problems later. And it was also found by other researchers in several other research papers. So that was not only our conclusion, but several other research articles also led to the same conclusions, let's say. What is also interesting is that the approximation errors around local optima can be significant. So as you remember, I present you the distribution of the error of approximation of the test set, right? But when our optimization algorithms found some candidates for the solutions, right? So candidates for local optima, then it turned out that the distribution of the errors is totally different. So first of all, it's not symmetric anymore, right? So here you can see we have 0, so it's not symmetric, because the errors were usually so our neural networks and other models tend to underestimate the ground truth values of the simulator, and of course it was no longer the normal distribution, and the errors were larger, close to the local optima. So that was a huge issue, because even if we found a good if we find a good setting for a given traffic conditions, then we cannot be sure that these settings will be good even in our mathematical model of traffic, in our simulator, and of course in the real world. And so these are just some reasons why, or at least these are our hypotheses, but we believe that these hypotheses are good. So these areas of the search space close to local optima are underrepresented in the training set. So of course, then it's hard to, and we shouldn't expect the neural networks to learn how to behave and how to correctly approximate the values close to local optima. And among the points that are near local optima, the optimization algorithms mainly find those that underestimate the simulator values, because for the values that are overestimated, then they are not considered local minima, right? So this is just a feature of the optimization algorithms. So these are our hypotheses why we achieved such a distribution of errors. And now about the solution, very interesting. And now we come back to the question from Itamar at the very beginning about taking advantage of the graph structure in our complex sets. So we managed to maybe not fully solve, but to achieve best results for these experiments using graph neural networks. So for these graph neural networks, so how graph neural networks work in general? So let's assume that this is our road network. So this is a simplification, of course, right? A very simple toy example of a road network. We have 5 nodes and 6 road segments. And then we built our graph neural network in such a way that for some layers, for let's say even ordered layers, we have neurons corresponding to the nodes, and for odd-numbered layers, we have neurons corresponding to the edges. And then we have connections between neurons in consecutive layers if and only if there is a connection between a given node and a given edge in the road network graph, right? So we built the architecture of the graph neural network based on the topology of connections in the original road network. So in some sense, we infer the domain knowledge about the graph, underlying graph structure. And what are the properties of such a graph neural network? So as you can see, such a graph is rather sparse, because in real road networks, there are not that many connections, right? There are not many connections between intersections. So this graph is sparse, so there are not that many parameters that should be tuned. So this is one thing. And another thing is that in some sense, the flow of information in such a neural network corresponds to the flow of traffic in the original road network. So we keep only those connections between neurons that seem to be important. So in some sense, it's similar to the L1 regularization in machine learning, which basically learns to or aims to allow the neural network to keep only the most important connections between neurons and just neglect the connections that are less important. So what were the results? So this mean absolute percentage error on the test set dropped again. So it was below 1.5 already. And the maximum approximation error on the test set dropped as well. And the similar minima were achieved in the simulation as according to the surrogate model, this graph neural network. And there was also lower approximation error near minima. And these are just answers why does it work, right? So significantly fewer parameters, so it's easier to train such neural networks. And we keep only the most important connections between neurons. So as I said, it's similar to N1 regularization in machine learning. So it's easier to generalize and it prevents overfitting. We also tested graph attention networks, but they did not produce better results. So the results were similar, but slightly worse. And now how this can be used for, let's say, real-time traffic, real-world traffic signal control system. So in general, first, when we collect some traffic data offline, we can perform clustering to identify different profiles of traffic. Then we can train some graph neural networks and then combine them with metaheuristics, with genetic algorithms or some other optimization algorithms to find some good, let's say, default settings that would be good for this typical traffic of profiles, typical profiles of traffic. But of course, in real world, the traffic is usually not typical. So we have many atypical situations, right? So in such situations, we need to somehow adjust the settings that we find to some new conditions. And of course, there might be some other adaptation algorithms used. So I can tell you that together with the TensorCell research group, we are now exploring reinforcement learning algorithms for this, right? So there might be some other approaches like using transfer learning or applying metaheuristics again. But in our current approach, we use reinforcement learning and we perform experiments on realistic road network in Malacca, in Malaysia, with 3 intersections. And we train our independent agents controlling traffic signals at 3 intersections, how to adapt the settings of traffic signals depending on the let's say, changing traffic conditions. Yes, Anne?
Thank you. I'm wondering how, so you're optimizing for the time a given automobile spends waiting to get through a signal. Is that right?
Yes,
okay.
yes.
So how did you get training data for automobile wait time?
Yeah. So as I mentioned, I've generated more than 100,000 simulations. So the data were from traffic simulator. As you can imagine, we are not able, because it's always in machine learning, it's best to have real world data. But in this case, it's not possible. You cannot collect, let's say, 100,000 different data sets, different signal settings for real traffic, because in real world, for given traffic conditions, you have only one settings. And even if you want to collect similar data for the same time, but the next day, the next day the traffic conditions might be different. So it's really not possible to collect such data from real traffic. But that's why I calibrated this traffic simulator, and as I told you, I achieved sufficiently good level of this GEH metric, which is considered by the traffic engineers as a good metric to say whether the simulator is accurate enough or not. And then when I was sure that the simulator is, let's say, realistic enough, I generated a large data set using the simulator. And then we trained neural networks based on the data set that was generated using a simulator. So these were not real world data, but data set generating using a traffic simulator.
Right. Thank you. And there were 42,000 cars that you were simulating
Yes.
for, did you say?
Yes. 42,000 during 10 minutes of traffic. Yes.
With 10 minutes of traffic at each light.
So this was a simulator of traffic in the whole Warsaw, or at least the area that was included in the simulation. But of course, this time of waiting was calculated only for this area with 15 intersections, right? Because we focus on this smaller area, right? But of course, even if we want to focus on a smaller area, we have to simulate traffic on a larger area because some new cars may start appearing during this 10 minutes of simulation, right? So it was necessary to simulate traffic on a larger area.
So in each data slice, so to speak, you were basically doing a snapshot of 42,000 cars and how they were distributed as along the roads, as among the 15 traffic lights?
So it was done a bit differently. So we assume that we have that for each of these, let's say 42,000 cars, we have their initial locations and we know the routes, right? So that was the assumption. And we run this more than 100,000 simulations just for different settings of traffic signals. So that was the only variable here, right? So we assume that all other things like initial locations of cars and the routes of cars were constant, were the same for all these 100,000 simulations. What was different, how different simulation runs varied was only the setting of traffic signals, actually.
Okay, great. And then it was just, you didn't actually factor into the calculations the networking effect as among the 15 lights, did you? They were each sort of, in other words, if light number 1 is set badly, then that's going to back up light number 2. Theoretically, know, so that would be kind of a complex.
Yes, that would be kind of a complex, but actually we also perform such an analysis later. I do not have it on slides, but thanks to using these graph neural networks, when we have these graph neural networks, so in these graph neural networks, as I said, some neurons correspond to the intersections with traffic signals, right? And then by performing we perform something like explainability analysis of this neural network to determine which neurons activate when, right? And then we are able to identify, let's say, which neurons or which intersections contribute to the output of these graph neural networks significantly, right? And which intersections are less important, let's say. So when you have this graph neural network in which neurons correspond to intersections or edges, you can do such an analysis. And we've even published one paper on this. I do not have it on the slides, but later I can share this research paper because we calculated the Shapley value, for example, to really determine which features are more important than the others, and so on. So this is another great property of graph neural networks, that the explainability of these graph neural networks is much easier than in case of feed-forward neural networks or some other architectures.
Okay, great. Well, thank you very much.
Yes. Okay. Yeah. So I told you that currently we are together with my research team. We are working on this adaptability, right? Because in the case that we started here, as I told you, we just assumed that our goal is to find good settings that would be set as constant for the 10 minutes, and we want to find good default settings for this 10 minutes of traffic, right? So that was the idea. But then we would like to adapt these default settings to changing conditions, just not to rerun all these optimization procedures each minute or so, because it's not feasible, because even the process of generating the data set is quite time consuming, right? We had to run 100,000 simulations, so we cannot do it every minute, of course. That's why we also started thinking about some other adaptation algorithms like reinforcement learning, and the results are also very good and promising. We haven't published paper on this, but I can tell you that the results are also quite good, and there are also many other research teams working on applying reinforcement learning to this traffic signal control as well, and especially multi-agent reinforcement learning, when there are different agents that learn how to control traffic at a given intersection or several neighboring intersections, and then they can communicate, exchange information about the number of cars waiting at each intersection, and so on. So this is very interesting research area. But anyway, at some point I also ask another interesting question. So can the proposed method be applied in other areas? Because you know, it seems to be quite general. We have a mathematical model based on cellular automaton. So this is a model of our complex process. We can run simulations. These simulations are time consuming. So then we applied machine learning models to approximate these time consuming simulations. And then we combine these trained machine learning models with optimization algorithms. So it seems to be quite general approach, and we do not. So maybe this graph neural networks was just one point in which we really just took advantage of the fact that we deal with road traffic, right? And the other parts of this pipeline do not depend on, let's say, the type of a complex process. And I didn't have to look far, because with the help of cellular automata, we can also model, for example, the development of cancer during radiotherapy treatment. And again, metaheuristics, like genetic algorithms, can optimize protocols, in this case, times and doses of radiotherapy administration. And one professor from my university, Professor Monika Piotrowska, published a paper about it, right? That how to identify significant multi-dose radiotherapy improvements by numerical simulations and genetic algorithm search. So another author is Simon Angus. So he's from Melbourne, from Australia. And their experiments were run on a supercomputing cluster in Australia. And Monika told me that when they ran these experiments, in total, it took more than 50,000 hours of running computer simulations, of course, on multiple processors, right? So it was not on a single processor, but they really had high performance computing cluster. But it took more than 50,000 hours, because the simulation model was even more complex than the model of road traffic in cities, as you can imagine. And it was also a stochastic model in this case. So they also, for a single protocol of radiotherapy, they had to run tens of different simulations to calculate the distribution of outputs and calculate some statistics, right? But again, it's a similar problem. So the goal is to find the optimal protocol. So this time not the optimal signal settings, but optimal protocols for radiotherapy treatment for a given cancer state. And the protocol of radiotherapy can be represented as a list of pairs, like dose and time of application. So this model was introduced in the paper that I told you about. It's a model of the so-called EMT6-row cell line. It was derived from a cell line that was isolated from the breast of a mouse with a mammary tumor. I think that this model was first built by researchers from Japan. And this model is just a stochastic multicanal simulation asynchronous cellular automaton. So it was introduced in the paper published already several years ago in 2009. But then there was an added calibration of multifraction irradiation model. And thanks to that, the model can be used not only to study various aspects of the tumor biology, such as tumor growth, but also response to radiotherapy. So that was what Monika and Simon did, and this model was calibrated. So they found good values of hyperparameters of the model to match the experimental data, real data from this mouse treatment, let's say. So you can see that there was quite good conformity of the distributions in this case, right? So there were not just single values, but there were distributions of values. So later, together with my students, so one of the problems, one of the reasons why the simulations was so time consuming was that it was implemented in MATLAB. So I asked my students to implement it in C++ and use GPU, and it already resulted in more than 700 speed up. So that was already a lot, and we've also tested that there is still quite good conformity between this implementation on GPU and the initial implementation in MATLAB. So as I told you, one of the advantages of cellular automata, comparing to some other models like differential equations, is that we can potentially parallelize the evolution of cellular automata on GPUs. It's quite natural. We represented cellular automata using grids, and it's a natural matrix representation for GPUs as well. So this is another advantage of cellular automata. And for each simulations, we just calculated something that is called, so this was a function. So this Pij denotes the considered protocol. So by protocol, I mean the set of times and values of the radiotherapy evaluated on a single tumor, because our goal was to find the robust protocol. So not the protocol, in this case, not the protocols that would be good for just a single tumor, but for, let's say, in this case, 10 similar tumors. So by similar, in this case, I mean that all these 10 similar tumors were derived by running a stochastic simulation starting from the same single state of a tumor. So after some time, the difference was not significant, right? And 2,500 is the maximum number of sites that could be occupied by the cancer cells. And Nij denotes the number of occupied sites, right? So that it was the number of sites occupied by the cancer for a given protocol and tumor after 10 days of treatment. So then this value was the value that we wanted to maximize. And again, we used genetic algorithms as before. And in this case, these were the only optimization algorithm that we used. So we ran many experiments with genetic algorithms and also had to implement dedicated crossover mutation operators. And thanks to accelerating simulations using GPU, and we managed to run much more experiments and find better protocols, right? So maybe I will not go into details here, but we used two benchmark protocols. So one was just 2 fractions of radiotherapy per day, 1.25 grays. So gray is the unit of the radiotherapy. With 6 hours or 18 hours time delays between doses. And in a second benchmark, there was 1 fraction per day, 2 grays per fraction every 24 hours. And there was a constraint for the sum of all doses, not more than 10 grays during a 5-day period of treatment. So maybe I will, because so the talk is already more than 20 minutes. So maybe I will just tell you that so in the first experiments, we considered constant doses, but there were different time intervals from certain sets and different sets for these 2 benchmarks. And there was also the second experiments when the maximum doses were the same, but we searched over a range of doses from 0.25 up to given maximum dose. So here you can see the values for the, let's say, first experiment. Just these are the values that were achieved just first for this first benchmark protocol that is still a benchmark in practice, as far as I know. And it's applied by doctors in many cases. And when we keep the same values of the dose, but just change the times and the time differences, right? The periods between 2 consecutive doses, then we can achieve better results. In this case, the higher value means that we have fewer cancer cells at the end. And when we apply genetic algorithms, the results were even better. That was the same for the second benchmark. Yes, so we relaxed the time differences. And the genetic algorithms were able to get even better results. So in the next experiments, the maximum fraction dose was incrementally stepped beyond 2 grays, as in the second benchmark, toward 4.5 grays, while keeping the same, the total 5-day treatment dose at or below 10 grays, of course. And in this case, we managed to achieve even better results, right? So this optimization procedure, again, gave us very good results. But the problem was that even using GPUs, the simulations were still time-consuming. So in order to accelerate them, we performed similar procedures. So we trained neural networks and some other machine learning models as surrogate models to approximate the outcomes of simulations, right? And then we first generated a large data set using computer simulations with 200,000 protocols of radiotherapy. Then there were several machine learning algorithms trained. And after training, these protocols were evaluated more than 100,000 times faster. So again, a few orders of magnitude, but of course, at the price of accuracy of obtaining the results, right? But what was also interesting is that the new loss function was introduced that is called margin ranking loss. And this is a very interesting loss function for training neural networks, and maybe also some other machine learning techniques, because this loss function is just designed to keep the order of input elements, right? So if we have 2 protocols of radiotherapy or 2 signal settings, and we know that according to the simulation, one settings is better than the other one, then we would like our trained neural networks or other machine learning models to keep this order. And we can see that actually this is something that is sufficient from a perspective of optimization, because we even do not want to or do not need to achieve exactly the same values as the simulation can give us for the same inputs. But we would also like to know whether two inputs or what's the relation between 2 inputs that we have, right? So which one is better? So that's why keeping the order is sufficient. So we tested many architectures of neural networks and like GBM again, and the best architecture was based on convolutional neural networks this time, with dilated convolution, skip connections, self-attention, and so on. And in general, the best results of optimization using genetic algorithms were more or less the same, but the results were achieved faster, right? But the process of generating the training set was time-consuming. And of course, we had some ideas for possible extensions and further research, like non-uniform distribution of radiotherapy doses in the tissue. So in these previous experiments, they were just distributed uniformly, adapting radiotherapy protocols using reinforcement learning. So similar approach as we do in case of traffic signal control, testing some other optimization algorithms, newer machine learning techniques and surrogate models, combining radiotherapy with other treatments like chemotherapy, and applying transfer learning to adapt the surrogate models to other cancer states. But and of course, the same methodology can be applied to other domains in which computations are time demanding. But there can be also some other theoretical questions, like how well can we approximate the evolution of cellular automata in general? And this is a very good question, because as you may know, some cellular automata are Turing complete. So I told you about Game of Life, which is an example. So Game of Life is a Turing complete cellular automaton. And there is also another popular, probably the minimum possible cellular automaton that is Turing complete. It's called Rule 110. And the idea was to just investigate whether we can accurately predict the evolution of this cellular automata. And there was also the third cellular automaton that was the deterministic version of the Nagel-Schreckenberg model, for which this stochastic rule was just removed. And it turns out that for the Nagel-Schreckenberg model, we can quite accurately predict the states of the cellular automaton after 50 steps. And in many cases, there is 100% agreement. But in case of this Turing-complete automata, it's no longer the case. So, and it seems that this is quite a difficult task for the neural networks to predict the future states of such cellular automata. So after this, I formulated a hypothesis that in general, approximating Turing-complete cellular automata is hard. By Turing complete, maybe that's something I should explain. I mean that this cellular automata, so these are the cellular automata that can, in theory, calculate the same things as any arbitrary Turing machine, right? So universal Turing machine. And in addition to the results that we obtained in experiments, this hypothesis was also suggested by the article that was published 3 years ago, that it's hard for neural networks to learn the game of life. And indeed, there was a totally different approach, but the conclusions were similar, that in general, for neural networks, it's very difficult to learn how to predict the future states of some Turing-complete cellular automata. But as we can see on the case of Nagel-Schreckenberg model, for some non-Turing complete cellular automata, it can be quite a simple task, right? So quite easy, right? So it's probably not that difficult. So it depends on the type of the cellular automaton. And in general, together with some colleagues working on automata theory, we even managed to mathematically prove that it's impossible to get double exponential acceleration of computations and keep the accuracy of predicting the cellular automata at the same time. And it's most likely it's also impossible to get exponential speed up, because otherwise we would have equality between these time complexity classes of the problems that can be solved in exponential time and in polynomial time by probabilistic Turing machine, which is unlikely to be true. So it hasn't been proven yet, but the researchers believe that this equality is not true. So most likely we are even not able to get exponential speed up for Turing complete cellular automata, of course. But for simpler automata, as we have seen, accurate approximation of evolution results can be much easier. So just to summarize the results, and then at the end I would just show a few slides related to quantum computing finally. I propose a universal method for optimizing complex processes, or at least some complex processes, using computer simulations, surrogate models based on machine learning and metaheuristics, and it has been tested for 2 processes: traffic control using traffic lights and cancer treatment using radiotherapy. And as you can see, these processes are from totally 2 different domains, but the results were similarly good, I would say. And in the meanwhile, we also propose a new architecture of graph neural networks. And of course, this traffic simulation framework software was developed and improved, and it has already found some interesting applications. And there are plans to use it in a smart city laboratory in Chełm in Poland, which is a new laboratory that is currently being established. And many metaheuristics, so many optimization algorithms have been tested with different settings, and it seems that these population algorithms, like genetic algorithms, give the best results. Large amounts of data have been generated. Most of them is, these data sets are now publicly available to enable further works. If you are interested, I can share with you the data sets that I've generated using the simulators. And I also proposed a definition of complex system and complex processes that I've presented at the beginning, because actually it's still not, so there is still no consistency between researchers on how to formally define complex systems and complex processes. And now at the end, finally, something about quantum computing, because I've told you about this traffic signal control using AI and surrogate models, graph neural networks, reinforcement learning, and so on. But it's also good to know that there are already QUBO formulations for this traffic signal optimization problem on a square lattice, which can potentially may lead to solving this problem using quantum annealing algorithms. I've read this paper. It's probably too complex to just present the results here. And of course, this is not my paper, but there was this QUBO formulation. So I will soon tell more about QUBO. But of course, this model that was used there is a very, very simple model of traffic, I would say. So it's even much more simpler than the model that I use in this traffic simulation framework. But anyway, this is a good beginning. This is a good start, in my opinion, because it already shows that we can formulate these problems using QUBO as well. So and then run quantum annealing to solve it. So for those of you who haven't heard about quantum annealing, so this is a procedure in which we first define our optimization problem as a Hamiltonian, and corresponding to an async model that can be encoded in a, let's say, quantum hardware. And first, we start from a ground state that is easy to prepare, for which the Hamiltonian is relatively simple. And then by changing the strength of a magnetic field slow enough, we transform the given quantum system to another quantum system. And if we do it slow enough, in theory, we should stay in the ground state. So if we were in the ground state of the, let's say, global minimum of our initial state, then in theory, we should still remain in the ground state at the end. And so this ground state corresponds to, let's say, the global optimum of our optimization problem. So this is the theory, because in practice it doesn't work like this, because there are some issues with this quantum annealing and adiabatic quantum computations in general. Because so first of all, this is based on adiabatic theorem, so we should ensure that this evolution of our quantum system is adiabatic, which is not easy to ensure in practice. And the other thing is that this change of the strength of a magnetic field should be slow enough, and there are even some mathematical formulas telling us how slow it should be. And it seems that for some problems, we might not be able to get an advantage, but still there might be some changes that will find good solutions. And this is and why this approach can work, because when we define our mathematical problem as a QBOD, this quantum unconstrained binary optimization, so this is the following formula, right? So we have multiple binary variables of degree forming a polynomial of degree at most 2, right? And here we just have some parameters, some coefficients. If, let's say, finding minimum to this optimization problem correspond to finding the minimum of our optimization problem that we have, then we can potentially encode this problem in a ferromagnetic, because this QBO also corresponds to the function of energy, so the Hamiltonian of the so-called Ising model, which is a model of ferromagnetism used in statistical mechanics. So in this case, these binary variables may correspond to spin up or spin down. So that's the idea, right? And then some parameters correspond to couplings, correlations or anti-correlations, and so on. So this approach is currently implemented in D-Wave's quantum annealers. And what I wanted to show you are two other cases, because the case with optimizing traffic signal control is too difficult to present it here. But there's another very interesting case that can be presented here, which was based on optimizing routes of fleets of taxis in Beijing. And now I would like to come back to this Brahe's paradox that I've told you about at the beginning, when we have many vehicles traveling from point A to point B, right? And I told you that if we build a new road, then it may turn out that the traffic could be worse. And it may happen in real world as well. But what is the problem? So one of the problems there is that the Nash equilibrium doesn't have to be the so-called social optimum. So the Nash equilibrium is a state in which all the agents that take decisions in our game, so in this case, the rules of the game are that each driver should just select a single route. So the drivers do not cooperate. So they do not synchronize themselves, and they just want to select the same road that is perceived by them as the best, the fastest. But if they start collaborating and they decide to split that, some cars may go through just one road, and some other cars may go through another road, then the traffic could be better. But currently we do not have such a synchronization, right? The drivers do not collaborate. But this approach proposed by D-Wave and Volkswagen assumes that we can do it. And what may happen if we do it? So what they did? So first they built a road network, and they have routes from real GPS data. So that this data set was called T-Drive, and that was the data set of routes of taxis in Beijing, in China, traveling from the city center to the airport. And for each car, for each taxi, they added 2 possible routes between source and destination. And it was assumed that cars may share road segments. And it was also assumed that the travel time is proportional to the function that is a square of a number of cars on a given route, which is, again, it's a simplification, but it's still quite realistic. And now we want to minimize the total travel time. So how to define it mathematically? So they introduce binary variables qij, where qij equal to 1 means that car I takes route j, right? So for each car, we have 3 possible routes, and each car should select only 1 route. So we need to ensure that this condition is satisfied, right? That for each car, we have exactly 1 route, so exactly one of these 3 possible variables qij is equal to 1 for a given I, right? And now let's assume that BS is a set of these variables with the variables qij associated with routes that share the street segment S in our road network, right? And what is the cost, the total cost of traveling through this road segment? So by this assumption, we can assume that it is a square of the number of cars on this route. So we can define it this way, right? So first we calculate the number of cars traveling through this route, and then we just calculate the square. So now the total cost, the total travel time, is the sum of costs for all segments. But again, we want to ensure that this condition is satisfied for each cars. So we want to ensure that this sum is equal to 0. So what we do in order to ensure it? So we introduce the so-called relaxation parameter, lambda in this case, and we should set a value of this parameter to be high enough, to be great enough, in order to ensure that any solver that finds a solution for which this sum is greater than 0 would not find this solution, basically, right? So this part will dominate, and this value would be so high that it cannot be considered as the minimum value for the total objective function. So that this value should be high enough to ensure that all the solvers, like quantum annealer, will find only solutions for which this part is equal to 0, and then we minimize the cost that we want to minimize. So that's the idea. And again, by analyzing this cost function, we can see that this is a Kubo formulation. So they managed to just encode it into a quantum annealer. They performed calculations with 418 cars. There were 3 times more logical variables. So the space of possible solutions was astronomical again. But as a result, a relatively small number of streets, there were a relatively small number of streets that were heavily occupied, and the time of computations was only 22 seconds. So in that paper from D-Wave, they didn't prove that it cannot be done faster using classical computer. I'm pretty sure that classical algorithms can do it equally good, but there was just no comparison at that time. But anyway, it was already one of the first demonstrations that quantum computers can, or quantum annealers from D-Wave can already produce something useful, let's say. It doesn't mean that they can do it better or faster than classical computers, but that they can produce something useful. And there's one more interesting case of applying quantum computing to optimize logistics. So in this case, I would not say that this is, let's say, the model of a complex process, because it's rather solving the vehicle routing problem and variants of vehicle routing problem. But anyway, it's also related to optimizing logistics. But I gave a talk about it 3.5 years ago, and I know that there is a video recording, so you can watch it to learn more. And I believe that the video recording from this talk will be also available on the same YouTube channel, thanks to Helen. Good, so that was all from my side, and I know that there were some questions on the chat, so I'll be happy to answer if we still have time, because I already took almost 2 hours. Let me maybe check the questions. Yeah, fun fact, quantum computing circuits. Yeah, there was a question about this Nash equilibrium named after John Nash. Yes, yes. So that's the same Nash equilibrium from the economy, for which John Nash received the Nobel Prize. But in transportation, it's called wardrobe equilibrium, but it's more or less the same, right? So we just assume that the participants of traffic, our drivers, are the agents who just play the game, and in each step of the game, they just select one of the possible routes. Okay, I don't see more questions on the chat.
There are more questions.
Yes, yes. Yeah, good.
At one point, you mentioned that you're not clear why the natural language models succeeded.
Yes.
And intuitively, not that I'm an expert on those models, I think there is strong coupling between the words in a natural language and a strong association or correlations that limits the different random, guesses. So that may be going faster to the desired optimum.
Can be, yes. I agree. So actually, this was also one of our hypotheses, that when we already train the BERT model or some other large language models on very large data sets, just due to the nature and due to the architecture, the topology of connections between different neurons, some values of weights of connections between neurons are already set in some, let's say, set to some values that are already quite good for further training, let's say. And actually that even in the natural language, there's already some structure, so it's not random. And introducing any structure already helps. So that's one of the hypotheses. Actually, I'm not sure, because at some point I stopped following it, but I know that, as I told you, there were some research articles with similar conclusions, right? Of course, the pre-training was different, the task for these language models were different, but the conclusions were the same. Maybe this problem has been already solved, and maybe it's already explained, but I'm not sure.
Okay, the traffic lights, the traffic, of course, was the major point in the report, mentioned many times. So I'm wondering if this simulation can do suggest non-equal cycles of the traffic lights, namely make the programs more sophisticated according to demand or density in the traffic light, whether it's heavy demand or light demand.
Yeah. Yes. Yeah. So. Okay. Yeah. So here I will go to another slide. Yeah. So these are the two slides I wanted to share here. Yeah. So in general, so the first method that I described can be applied to some certain traffic conditions. So I totally agree that if traffic conditions are different, we cannot apply the same settings that were considered as good and default for some traffic settings that for some traffic conditions that we initially had. So for this case, my idea is that first we should identify these typical profiles of traffic, like Monday morning at 8 a.m., right? Because there are some recurrent patterns. There is a noise. There is a lot of noise, and there's a lot of fluctuations, and traffic is never the same when we compare it even in 2 consecutive days or the same days in the week. There are some differences, but there are also some recurring patterns, because people usually travel from more or less the same areas to similar areas as well. They travel to work, they travel to school, and they usually select similar routes and similar modes. So of course there are some random changes, but there are some recurrent patterns. So my idea was that first we can we can identify this, let's say, typical profiles of traffic, typical patterns, and find good default settings for this default patterns. And then when there is when there are some changes, when there is a noise, we can apply this reinforcement learning, for example, to dynamically adapt traffic signal settings to some new conditions, right? To differences comparing to the typical profiles of traffic. So that's the idea.
Adaptive to the situation.
Yes, exactly. And reinforcement learning is very good for this, because in reinforcement learning we also have simulation environment. We have some states of traffic, and we teach our agents to perform good actions for a given state of traffic. And these actions can be like extend the duration of a red signal by 5 seconds, right? Or switch to another phase. So these are the typical actions. And in the current experiments, we haven't published it yet, but the results are very good as well. So we've already managed, just a few months ago, I think in May, we managed to outperform a default, one of the most popular algorithms in traffic engineering that is called Webster's method. So this is an algorithm for controlling a single intersection. And the reinforcement learning models that we've trained managed to outperform this Webster method that was designed by people, by human experts, by traffic engineers many years ago. I think that 50, maybe 60 years ago, but it's still used in to control traffic at some intersections. What about weather conditions? There is a question. So again, adaptability, but anyway, we haven't investigated it. But of course, in case of weather conditions, I believe that the whole traffic model would be different in general. So we would need to introduce some changes at the level of something like this microscopic model that is behind, right? So the cellular automaton already. That's my guess. We do not have data. We do not have such data to calibrate such models. So as I told you, we've run experiments in the environment, simulation environment, that is a really huge simplification, right? So it's much simpler than real world conditions, but as I told you, it's already very complex. And in particular, this optimization problems of traffic signal setting is NP hard, even for such very simple traffic models. And now you can imagine that when we have some different weather conditions or some other effects, then the problem just becomes more complex. Okay, I can see that Ram has raised his hand, so maybe Ram would like to say something.
Oh, thanks. I actually just typed up a comment, but it's there seems to be some of the things that you mentioned just made me think that there may be an extension of your research in organizational dynamics as well. And that the problem that one observes is that when you optimize at a local level on a team, you might get suboptimal outcomes at a global level or a high level in a business. Vice versa, when you try to optimize at a top level, then you cause suboptimal performances or lower level. And so there may be ways to identify maybe not exactly how to optimize your organization, but what levers you might try to pull at the different levels in an organization. So
exactly. So that's also something that I started. So so based on also what Itamar said at the beginning, it's a good idea to run experiments on the smaller networks, but then when we have good solutions for subregions, then we have to combine them to just generate a solution for the whole region. And it seems that it's also not that easy. So I cannot say that I have investigated in details, but based on the experiments, I think that I had one slide here about it, where it was. I think it was somewhere here. Yes, that when we performed optimization only on smaller area and totally neglected intersections in neighboring areas, then the outcome was that the traffic was much worse in other areas. as well. So it's not that easy to. So it's probably not sufficient to just optimize traffic signals at subregions totally independently. But I believe that in general there should be some hierarchical solutions, because for very large road networks, so in Warsaw we have 800 intersections. I'm not sure how many intersections. Sorry, 800 intersections with traffic signals. I'm not sure how many intersections with traffic signals are in Washington, but I'm pretty sure that in New York there are thousands. So the scale is even higher. But anyway, as I said, when you have two different districts, then the intersections or the impact of intersections in one district is not on the traffic signal, on the traffic situation, and totally different district, like many miles away. It's not that high. So it's for me it's quite natural and reasonable to try to solve the problem for smaller areas and somehow produce the solutions, or just maybe adjust the solutions. Maybe have another AI agent coordinating different AI agents. So there might be AI agents controlling traffic in subregions, and then there might be something like a master agent adapting somehow this other AI agents at smaller level. So I believe, so I cannot prove it scientifically, or at least I haven't proven it scientifically, but I believe that introducing some kind of a hierarchy would give an advantage here. There's also a question about autonomous vehicles, so I would also like to tell a few words about it, because when you have the autonomous vehicles, then of course the traffic would be different. Right, so here we have these traffic models, but it's a traffic model for human driver. I'm not sure if we would have this let's say stochastic effects in case of autonomous vehicles. Maybe, but maybe not. I'm not sure. And one of the advantages of autonomous vehicles is that I believe that in case of autonomous vehicles, we should be able to model traffic more accurately, so that there will be better conformity between the simulation outcomes and the real-world data, because we can collect from the autonomous vehicles not only information about their current location and current speed and acceleration, but we can even take the information about the future routes, and maybe we'll be also able to get the exact algorithm of drive. And then we can just simulate this algorithm in our traffic simulation. We cannot easily see, so this is a model simulating the human driver's behavior, but as you can see, it's a very simple model. It's for sure, it's too simple. But in case of autonomous vehicles, if we know the exact if we knew the exact algorithms of drive, we can potentially simulate these algorithms in a simulation environment. So I expect that the traffic simulations should be just better, should have greater conformity with real traffic. There's another question. Is your work considered a use case of a physics-informed neural networks? I'm not sure. I think I haven't heard about, or I haven't heard the name physics-informed neural networks, but in some sense, perhaps, because, so we have these graph neural networks in which the architecture of the neural network was designed based on some data domain knowledge, right? So based on the information of how the railroad network is designed. And actually, I can tell you that so we have two publications on this, and we even proven that it really matters. So these good results that I presented later were not achieved by accident, but when we built a graph neural network based on a different road network topology than the topology that was used to generate the data set, the training set using simulations, then the error increases, the error of approximation increases. So we've formally scientifically proved that introducing the exact road network structure really matters. And for this, we can say that there is a scientific proof for this. Yeah, so there's a question about big data and using traffic data from the past years. So in some sense, so I partially used real-world data, of course. So here, as I told you, I collected data from urban road authorities in Warsaw, but there were information about origin-destination matrices several years ago with information from where to where people travel. There were information about traffic congestions, so data from some traffic detectors, and information about travel times. So based on that, I was able to calibrate the model so that the conformity with reality was satisfactory, right? So there's this GEH matrix that is used in traffic engineering to say whether a given simulation model is good or not. But when it goes to, or when it comes to different traffic signal settings, as I said, in the real world, you have only, for given traffic conditions, you have only one setting of traffic signals, right? So there's just no option to get such data as we needed in this case. That's why it was necessary to obtain data from simulations. But I do not say that this is the only possible approach to traffic signal control. Definitely not. There are many other approaches that do not use simulation data, but use only real-world data, let's say, right? But in this case, in this approach that I've studied, it was necessary to calibrate the simulation model and then generate very large data set using a simulator. Yeah, there was a question how quantum computing helps to solve traffic problems when compared to classical computers. So as for now, in my opinion, quantum computers are not better than classical computers for this case. Yeah, so first of all, the contemporary quantum computers are still relatively small and noisy, so even encoding such optimization problems is difficult. So even for optimizing logistics, we're able to run experiments for relatively simple cases, for relatively simple scenarios. And this case that was presented by D-Wave and Volkswagen was run for, there were 418 cars. And of course, the space of possible solutions was large. But in their research paper, they didn't prove that the same results cannot be obtained using classical computers. And I'm based on my experience, I'm quite confident that it should be possible. So I don't expect that currently quantum computers can already outperform classical computers, but perhaps in the future it will be possible. We'll see.
So, Pawel, what about genetic algorithm? What optimization problem it has?
So coming back to the genetic algorithm, so in this case, so let's focus on this case of traffic signal control. So first, these traffic signals were just represented using genotypes. So formally, in a code, they were just represented as large vectors of numbers. And the numbers corresponded to settings of traffic signals, right? So they were just large vectors. In consecutive iterations of the genetic algorithm, first, these vectors were put as an input to this traffic simulator or to the trained neural network that produced the output. And then thanks to that, we were able to compare different settings, different vectors. And then the best settings were selected. And then there was crossover. So parts of one vector were just mixed with parts of another vector from the selected best vectors, of course. Then there was a mutation. So with some probability, some values in these vectors were changed, which produced a new set of possible genotypes. And after multiple iterations, like hundreds of iterations, we were, so even earlier, we were able to observe that after a few or tens of iterations, we are already able to produce better settings of traffic signals than the best settings in the randomly generated large space, right? Large set but the set that was generated randomly. These algorithms usually needed hundreds or sometimes even thousands of iterations to converge.
Oh, that was the problem. Okay, thank you.
There's a question about the code. Yes, I can later share a link. So Helen, I will share the slides and links with you so you can distribute them. Yeah, so there's a good comment about traffic signal controllers for trains and planes, that they are better because there are no free agents. That's correct. So I also expect that with autonomous vehicles, we should be able to manage traffic better. Question about present. Yes, I will share the slides, and I believe that this talk is recorded, so there will be a video recording on our YouTube channel available.
Pawel, just to say thank you very much for your presentation.
Okay.
This is an unusual presentation, took more than 2 hours.
Yeah, good questions, yes.
Most of us still here, listen to you because of the quality of your presentation.
Okay. Thank you, Cayetano. Good to hear that. Thanks. I'm happy that you liked it, you enjoyed it, and yeah, I'll be happy to share the slides and links later. Okay. Helen, do we have more questions or should we finish?
So far I don't see more questions. I just see it was very energetic and interesting the whole time. I keep seeing good comments coming through.
Good. Okay.
So do you have more questions to ask online? So if not, let's end the meeting. And if you have follow-up question, you can reach out to Pawel for more questions. Thank you for all coming.
Thank you.
Thank you very much.
Thank you. See you next time.